Hello students, in this lecture we will see nodal analysis and then we will solve numerical based on nodal analysis. Now before proceeding towards nodal analysis, let's say such type of circuits are there. Let's say first circuit over here. The voltage at this point is Vx, another point is Vy, and you are assuming that the current is moving towards right. Then I can be written as current and the value of the resistance is R. I starts at Vx, ends at Vy, so destination voltage has to be subtracted minus Vy divided by the resistance R. Okay. If you assume current is moving towards left over here in the first circuit, then I can be written as current starts at Vy, ends at Vx divided by R. Always the destination voltage has to be subtracted. Now for the second circuit, let's say the voltage at this point is Vx, over here it is Vy, and the battery is Va. Battery value is Va and the resistance is R over here. And you are assuming that the current I is moving towards right. Then I can be written as current starts at Vx and you go ahead. The leading sign is negative and the value of that source is Va. So Vx minus Va, and you reach at the destination. Always the destination voltage has to be subtracted. So minus Vy divided by the resistance in this path, that is nothing but R. For the third circuit, let's say at this point the voltage is Vx, over here it is Vy, and two batteries are there. Let's say one is of Va, another value is another voltage source is value Vb, and there are two resistances R1 and R2. Now how to write down I over here? Let's say you are writing the current I which is moving towards left. This is my assumption. Okay. So current starts at Vy. You go ahead. Leading sign is positive and the value is Vb. Go ahead. The leading sign is negative, so minus Va, and then you reach at node X, so minus Vx. So you have accounted all the voltage difference over here in the numerator divided by the resistance in this path, so that is R1 plus R2. So current can be written as voltage difference divided by the resistance. Now we will see the procedure to solve the problem on nodal analysis. Basically the nodal analysis is based on KCL, and KCL says that summation of outgoing current is equal to summation of incoming current. So one can say that the algebraic sum of the currents meeting at any junction or node is 0. So whenever you are writing KCL over here, the next line you have to write down summation of outgoing current is equal to summation of incoming current. Now first of all you have to identify the nodes. The first step is identification of node. Now what do you mean by node over here? Node is a junction where more than two elements are connected. Okay, that means three or more elements are connected. So can this point be a node? No. Here at this point only two elements are connected, two branches are connected. One end of 6 volt and another end of 3 ohm is connected. So this cannot be a node. Can this be a node? Yes, this can be a node because there are three elements are connected. So first of all I am highlighting the nodes over here. Can this be a node? Yes, this has to be a separate node because with respect to this node there is a resistance over here. You can expect current through 4 ohm, so voltage will be there across 4 ohm. And naturally this voltage at this node and voltage at this node, this junction will be different. So there are two nodes. Can this be a node? Yes, this can be a node. Okay. So there is one more node over here. Can this be a node? Yes, this can be a node. But if you see here between these 2 points, there is no element over here. That means graphically these 2 points are different, but electrically these 2 points are same. So this form only one node over here. So there are 3 nodes in this given circuit. Okay. So first step is over. After this the second step is identification of reference node, or you can say ground node, or another name is datum node. Datum, D-A-T-U-M, datum node or reference node. Now which node has to be selected as a reference node out of these 3 nodes? You can select any node as a reference node, but for our convenience we will select a node with a maximum connection. So you can see at this node 1, 2, 3, 4 connections are made. So we can select this node as a reference node. So we'll mark that as a reference node. So reference nodes have to be marked like this one with a symbol of ground. 1, 2, 3. Okay. So the voltage at this point will be 0 at this node. So that is the second step. First step, I am repeating once again, identification of a node. Node, it is a junction where more than 2 elements are connected. So that is the first step. Second step is marking one. The second step is selecting one of the node as a reference node. Then third step is assigning the variables for the voltages for the remaining nodes. So here I am assuming the voltage as Vx and here I am assuming the voltage as Vy. So right now I have two unknowns with me, and those two unknowns are nothing but Vx and Vy. To find out these two unknowns, I require two equations. Now how to obtain these two equations? So you apply KCL at node X, you will get one equation. You will apply KCL at node Y, you will get another equation. And then you will have two unknowns and two equations. You can solve them simultaneously to find out those unknowns. Okay. So we will actually solve this numerical over here. So the problem statement is find the current through 6 ohm resistor using nodal analysis. Okay. So the first step is identification of node. So the first node I have identified over here. The second node I have identified over here. And the third node is over here. You can say this is one and the same thing. Now out of these three nodes, one node has to be treated as a reference node or ground node. So I am treating this as a reference node over here. Now after this, assign the variable for the voltages for at this node. So the voltage at this node is Vx, while at the other node I am denoting as Vy. So third step is over. After this, you want these two equations. So those two equations you will get by applying KCL at those individual nodes. So I am writing over here KCL at node X. Now at this node, three branches are connected. And when you are writing KCL, the next term is summation of outgoing current is equal to summation of incoming current. Now how to write down the three currents associated with this node X over here? First of all, you observe this thing. Remember this thing. Is there any current source connected to node X directly? No. There is no current source connected directly to node X. So that means I will assume all the currents as outgoing. This will simplify our thing. How? That we will see. So whenever current source is not there, you can assume all the currents as outgoing. So three currents will be outgoing. So the leftward current, which is starting at node X and ending up over here, you have to write down. So this current can be written as current starts at node X, go ahead -6, end up over here, so -0. Being a first numerical, I am explicitly writing the voltage at reference node over here, that is 0. And the resistance over here is 3. We have written such type of current in the first slide. So this current I have accounted. Now this downward current through 6 ohm I have to write down. So that current can be written as Vx the current ends at 0. So -0 divided by 6. Summation means addition of these currents. And the next rightward current you have to write down. You have to start at node X and you have to end up at another node. So Vx ends at Vy. Okay, divided by 4, and that is equal to, I am not assuming any incoming current over here, so this is equal to 0. So you will get one equation in terms of Vx and Vy. The best thing is to take LCM. So LCM of this one is 24. You can easily calculate that thing. So multiply throughout by 24. So I will get 8Vx minus 48 plus 4Vx plus 6Vx minus 6Vy is equal to 0. Though you have multiplied by 4 because of the LCM, the right hand side still it will be 0. So you can write down this in equation format. So I will have 18Vx minus 6Vy is equal to 48. How to arrange the equation? Vx, Vy, these unknowns on one side and constant on another side. Now I have to obtain second equation. So I will apply KCL at node Y. And whenever you write down KCL, the next line you have to write down summation of incoming current is equal to, rather summation of outgoing current is equal to summation of incoming current. Okay, I prefer writing outgoing current first and then incoming current over here. Simply, it will simplify the thing. Now to node Y, is there any current source connected to node Y? Yes, there is a current source connected to node Y. What is the direction of this current source? Towards node Y. So this is incoming current. So this current I can treat as an incoming current and I will directly write over here. Whenever you are writing KCL, every term should be current. Either the voltage difference divided by resistance or the current term as it is over here. So here I am writing that incoming current over here. If they would have given a reverse direction, that is going away from node Y, I would have written 5 on LHS, which is outgoing current. So this branch I have accounted. Now remaining 2 branches, I will assume again outgoing current. Because of simplicity, you can assume outgoing current. So the leftward current you can write down as Vy ends at node Vx divided by 4. And this downward current you can write down as current starts at Vy ends at reference, that means 0 divided by 4. LCM is 4, so this will give me Vy minus Vx plus Vy is equal to 20. That means you have multiplied throughout by 4 because of LCM is 4. And this will give me equation as minus 1 Vx plus 2 Vy is equal to 20. And this is my equation number 2. Now what is the advantage of assuming the currents as outgoing over here when you are applying KCL at that node? If you assume the outgoing currents at this node while applying, let's say at node X, you will have coefficient of Vx as positive while the coefficient of Vy will turn out to be negative. Again you can see here at node Vy, this current is incoming, so that is not a problem over here. But remaining 2 currents I have assumed as outgoing, so that's why I am getting the coefficient of Vy as positive while the coefficient of the other voltage I am getting as negative. So that is how you can easily check the thing. So there are 2 equations and 2 unknowns. You can substitute these coefficients and constants in the calculator and you can calculate Vx and Vy. So Vx turns out to be 9.33 volt and Vy turns out to be 14.67 volt. The problem is not over yet. You have to calculate current through 6 ohm resistor. So current through 6 ohm resistor is equal to, there is 6 ohm resistor here and you can assume a downward direction. You can assume downward direction. That means current starts at Vx, ends at 0 divided by 6. So this, and that means I am moving downward. Let's say if you are decided to move upward, then this will be 0 minus Vx by 6 and the current will be upward. Right now I have assumed downward current. So this will give me 9.33 by 6 and downward current, and which will give me answer as 1.555 ampere downward. Thank you.